In this video, I'm going to look at whether the converse of Fermat's little theorem is true. So first off, we need to establish what do I mean by the converse. Well, let's say we have a true statement in the form A implies B. So what this means is, if this is true, then if A occurs, then we can be sure that B will occur too. Now the converse of A implies B would be B implies A. So essentially what I've done is swap the A and the B around. Now, you can never assume that the converse of a statement is true. However, if this statement was true, then it would mean if B occurs, then we could be sure that A is definitely going to occur. Now, let's relate this to Fermat's little theorem, okay? Because RA would be the idea that where A is an integer and P is prime. And then RB would be what must be true if A is true. So that would be the A to the power of P subtract 1 is congruent to 1 mod P. Now let's investigate whether the converse of that is indeed true. So the idea that if we can find a congruence relation of this format here, can we be sure that A is an integer, which it must be if this statement is true, but more importantly, is P definitely prime? And what you'll find is that even if you find a congruence relation of that format which is true, you won't always be able to assume that P is prime. So in other words, the converse of Fermat's little theorem is not true. Now a counterexample which disproves the converse of Fermat's little theorem would be the idea that 2 to the power of 340 is indeed congruent to 1 in mod 341. And this statement is in the format of what we're used to seeing for Fermat's little theorem, because we've got our integer A, which is 2, and then our power be 340. That would be our P subtract 1, meaning P must be 341, which we can see written over here. And of course, we've also got be congruent to 1 here. So it perfectly matches with what we'd expect if we were using Fermat's little theorem. However, the 341 is actually not a prime number, because we can write 341 as the product of 11 and 31, meaning that 341 is a composite number. So therefore, that is a counterexample to show that the converse of Fermat's little theorem is not always true. Now, what we can say is that our composite number, 341, is an example of a pseudoprime base 2, where the 2 is our value for A that was in our congruence relation. Now, why would we call it a pseudoprime? Well, we'd say that because it's not actually prime, and the word pseudo can mean fake or not genuine. However, the 341 satisfies the congruence relation, A to the power of P subtract 1 is congruent to mod P, okay, where that value of A is 2, and we'd call A the base. So we can write out a general definition for a pseudoprime in a given base. So our general definition is that if X is a composite number, and the following congruence relation is true, so A to the power of X subtract 1 is congruent to 1 mod X, then we can say that X is a pseudoprime base A.